Okay. Let's have a look at the next section then. So before I do that, you should have a look at question 2 here at the very least, and think about how you would integrate that, linking back to the different situations we've seen so far. Okay, so we have some of this sort of reverse chain rule over here with the numbers and compensating. We have the same over here as well. On this one, you divide by a third, which is the same as multiplying by 3. Um, sec squared becomes tan with the same idea. Cos becomes sine with the same idea. Sectan becomes sec, and cosec squared becomes minus cot. Okay, the top ones here, you need to use cos double angle and sine double angle. Okay, so we've sort of seen already this idea of like considering and then scaling up or down to integrate. Okay, so we're going to do the same thing now, but instead of doing it with instead of just sort of doing that when we have something like 3x and then using like a third, we're going to deal with slightly more complicated situations. So this one here, I'm looking at this as an x on the left and then a bracket to the power of 3 on the right. And what I notice is that there's a relationship between x squared plus 5 and the x on the outside. And the relationship that I'm looking for is the fact that this bit here inside the brackets differentiates to something pretty close to the thing outside. At least the powers sort of work, which is really what I'm looking for. So what do I mean? Well, the reason why I'm doing this is this bracket, if I just concentrate on the bracket for a moment and I say that integrated would become the power of 4, right? We'll put the quarter on the outside. Let's just look at what happens. So that's what I think it might be. With a plus c, I won't write that down. What would happen when I differentiate it? Just look. Well, the 4 and the quarter cancel out. So it will be bracket to the power of 3, which matches what I've got. But then there would also be a chain rule, because bracket to the power of 4 is the outside bit. The inside bit would be 2x. And you notice this thing here and this thing here are very, very close. It's almost perfect. The only problem is this would become 2x bracket cubed, and this is just x bracket cubed. So in other words, this result up here is 2 times too big. So I would need to divide that by 2. Well, the thing it came from would need to be divided by 2 then. So I should have 1/8 bracket to the power of 4 plus c. A quarter divided by 2. A quarter divided by 2 is the same as saying an eighth, okay, if you're unsure about that part there. So it's very similar to the thing before. Like you try and integrate it, you pick the complicated bit. It tends to be the bit that has a power, okay? You pick sort of the complicated looking bit and you differentiate that, and then you look at what you get you'll get an extra bit because of the chain rule. You'll get an extra bit like the 2x here, and you'll compare that to what is here already, and then you might need to scale it up or scale it down to make it work. So let's do another one. So sine squared x, I said you need an identity, but for cos x sine squared x is actually easier. Look what happens. So if you try making it sine cubed x, I'm going to write it like this. I always prefer it this way. Well, you need to do a third. That's your guess. That's your good guess. Well, if you differentiate that, the 3 and the third will cancel. And you will get what? You'll get sine squared x, but then you'll have a chain because of the middle as well, times cos x. Well, if you look at that, that's exactly the same as that, which means this must be the answer, that plus c. So you consider the more complicated part, I'm going to call it here. You integrate that and you differentiate and you check your result. Does it need to be scaled up or scaled down? This one fits perfectly. Okay, so that's a really, really nice result. One more. So hopefully you're starting to notice now the pattern is that x squared plus 1 differentiates to something with x in it. That's why this works. So x squared and then x to the power of 1. That's why that works. X squared, x to the power of 1. That's why this works. Sine differentiates to cos. That's why this works. Okay. So you want to look out for when you have a bit that looks a little bit complicated. But then the part that would chain, if you see like a multiple of it elsewhere in the expression, that's when you want to use this. Okay, so here you try this one here, and maybe to your surprise, it works exactly. So actually, that's all you have to do. Okay, so these expressions, some of them look really hard, but because the chain rule is at play, sometimes the answer is surprisingly simple. So a couple more. Can you spot again? There's that relationship between those. Okay. Now the numbers, x cubed becomes 3x squared, but that's x squared. That's not a problem. Okay. We can fix the numbers of scaling up and down. We can fix that easily. We can't deal with the power difference easily, though. Here as well, we've got an x squared. 1 is not a problem. That will disappear. And we've got an x. I know x squared becomes 2x, but the x squared and then the power beneath it, that's the part that's really important. Okay. This is a more sort of formal way of thinking of it, but you don't really need to worry about this too much. All it's saying is if the derivative of the thing is sat next to it, even if there's a number or not, um, it will often integrate to just that thing to the next power. And then maybe there might be some division, there might be some adapting based on the number. Okay. So here we look at this, and first of all, we think of this as 1 over x cubed plus 1. So natural log of x cubed plus 1. When you differentiate it, what will you get? You will get 1 over x cubed plus 1, but you will get a chain here, and this will become 3x squared. It's 3 times too big, so you must make your answer 3 times smaller. Okay, well done if you're sort of understanding this idea already. It's not simple at all. It does take quite a bit of practice. So e to the thing, your first idea might be, well, let's just integrate it. E to the thing becomes e to the thing. When you differentiate, you will get e to the thing multiplied by 2x. What is the problem? The problem is this is 2 times too big. You'd need to divide it by 2 to get to this. So the thing that you tried, you also have to divide it by 2 as well. So this should be your answer. A half e to the blah, blah, blah plus c. Okay. So some quick fire questions. I'm going to just reveal them. I want you to pause and to have a go. You don't have to do these in your head at all. In fact, I wouldn't try and do these in my head. Certainly not yet. Maybe later, but not yet. So have a go at those. Pause the video and we'll have a look together. Okay, x cubed differentiates x cubed cubed x to the power of 4 minus 1 differentiates to 4x cubed completely. So you'll get a really nice result here. No need to scale up or down. It fits perfectly here. The sine part. So in the denominator, try natural log of sine of x plus 2. And if you do that, the middle, this bit here, this input, will differentiate through the chain rule. And you'll get cos x, and it fits the pattern as well. Here, start with the e part. So try e to the sine x and see what e to the sine x differentiates to. It differentiates to cos x e to the sine x. So e to the sine of x is correct with the plus c, of course. Here, try the bracket to the power of 7. So bracket to the 7 should become 1/8 bracket to the power of 8. And sine of x minus 5 should differentiate to cos of x. Okay, just lots and lots of practice. If this doesn't make sense yet and you're not sure, go back, pause, do them, and make sure that pattern clicks. The pattern that you're looking for is that this differentiates to a multiple of this. This differentiates to a multiple of this. This differentiates to a multiple of this. I say multiple because if the numbers are not right, that's fine. You can fix that. Okay. So this one here, try bracket to the 8. So 1/8 bracket to the 8. The middle will differentiate to 3x squared. You have x squared. So the number's going to be a little bit different this time. It's not quite what you think. So this 1/24 will be made up of your 8th for your bracket to the 8, but also 1/3. Because when you differentiate this part in the middle, you'll get 3x squared, but you have x squared. You need to scale it down by 3. You need to multiply by 1/3. Okay, and one more here. This one has the x here on top, so you just rewrite this all with the power of -3. Okay. Okay, so this part differentiates to a multiple of this part. That is the key idea that you're looking for. No natural log for this one, please, because there's an x in the numerator. And well, also, and because we have a 3 here. When you have things in the denominator, there should be no power on the denominator as a whole. Okay, that's quite a common mistake, that one there. So if you went straight for natural log, we don't want to go for that one there. Natural log would be okay if we had like 1/x squared plus 5. That's fine. The problem here is that it was x squared plus 5 to the power of 3. So that needed to be changed to -3. Okay, so let's have a look at a couple more. So sine to the power of 5. Well, hopefully by now, but what are we doing here? No, we're just differentiating. So we're looking at what happens when we differentiate. So, yep, we get that result there because of the chain rule. That's why if you have like sine or cos to a power, and then you have the other one, the cos or the sine next to it, actually you can integrate that much more easily than sine squared, cos squared, and so on. So that's just an observation from differentiating sine to the power of 5. If you differentiate sec to the power of 5, something quite interesting happens. So you'll get 5 bracket 4, yeah? And then there's a chain rule, you get the middle, you get sec tan. And if you put these sec parts together, you get this result here. So when you differentiate sec x to the power of 5, it looks like the power stays the same. Well, I mean, the power does stay the same. And you create these tan parts here. So it's just one to be aware of, that sec has an unusual sort of pattern when you differentiate it. So when you're doing this one here, you might be surprised by the result. You might try, for example, you might try sec to the power of 5 as the thing that you think should integrate to. But if you test that, what did you get? Well, when you differentiate that, we've got the result up here. You get 5 sec 5 tan x, which is not that thing there. So don't try that one. Try this one. Try sec to the power of 4x. And you will get 4 sec x to the power of 3. That will be the outside. And the inside will be sec x tan x. If you clean all of that up, you will get 4 sec to the power of 4x tan x. So sec to the power of 4x gives you this result here. But we don't have that result there. We have a quarter of it. So a quarter of that will give you a quarter there. So a quarter sec to the power of 4x plus the c. So it's an observation about sec. Sec is an unusual one. If you're trying to integrate it, try making the power the same. So pause the video there and have a go at those questions on the board. They will take you a fair bit of time. So a multiple of its derivative, cot, yep, a multiple of its derivative. Tan 2x, a multiple of its derivative. You can sort of see what I'm getting at. This one here, you can do this one a few different ways. So bracket 6 and so on. This needs to be to the power of -3. Okay, this part here minus 3. So this is like your best guess. That's what they're saying. Okay, that one, yeah, you just need to scale that one with a half. That needs to be scaled with a half. That goes with the quarter. And this is one of the results for this one here. There are other solutions to this one. If you try the sec to the same power, you'll get that result there. Okay, so getting a bit more complicated. The good news with this one is as we go into substitution for the next topic, you will see how these questions can actually be done with the substitution. So if you find this is just a little bit too much ad hoc sort of stuff going on in your head, um, you might enjoy substitution quite a lot. But obviously, we have talked about the benefits of reverse chain rule, which is the speed. Okay, it's much faster to do, and as long as you check that your results actually work by differentiating them again, you should be okay.